Hi everyone. In this video, we're going to look at two variable inequalities. So we've looked at a lot of different types of inequalities so far, but they've all been one variable. So we're essentially solving for a domain, a range of potential values for x, and our answer can therefore be expressed as a domain. This is a little bit more complicated now once we start getting into two variable inequalities. We'll start with some simpler ones, but the idea is essentially much like with one variable inequalities, we start by considering the associated equation. So in this case, I'm going to consider the equation y equals 2x minus 4. This equation is part of this particular inequality because I have y is greater than or equal to, so the or equal to does include this equation. But we know that this equation represents a line. More specifically, all of the points on that line are coordinates for which the x and y values satisfy this equation. So the points on that line are also going to satisfy this inequality. So let's go ahead and draw that line. Y equals 2x minus 4, so I have a y-intercept at negative 4. Negative 4, slope of 2. So I'm going to end up with a line that looks something like this. And right off the bat, I have now an entire set, an infinite set of points that satisfy not only this equation, but also this inequality. And there's really no way to express this using set notation or interval notation. The two ways of expressing this algebraically are by writing the equation, y equals 2x minus 4. That tells me the relationship between the coordinates of x and y for every point on this line, or by graphically representing the equation. Drawing this line is one way to represent the solution set of x and y values for this equation. Now, in addition to the points on the line, I've now divided this plane into two regions, two half planes. There's the region above the line and the region below the line. You could think of it as the region to the left and the region to the right, but we're not going to think about it that way because we're contemplating what's happening with y. So as I go in a little further, I'm looking at now the inequality where I'm saying y is greater than or equal to 2x minus 4. So in other words, while the points on this line are where y is equal to 2x minus 4, I'm also going to allow for points where y is greater than 2x minus 4. So if I consider a particular value of x, so let's say x equals 7 here. So there's a vertical line where every point on this line has an x value of 7. What I'm wanting to include in this solution to this inequality are all of the points where the y value is greater than or equal to 2x minus 4. So the green point, the point on the line right here, that's where y is equal to 2x minus 4. 6 is equal to 2 times 5 minus 4. Everything above that line is where y is greater than 2x minus 4. And everything below that line, or that point, the green line that I've drawn, is where y is less than 2x minus 4. That's why I'm looking vertically here, because I'm considering where is y bigger, where is y smaller than the y value on the line. So since I'm looking for where y is greater than or equal to 2x minus 4, I'm looking at this entire region above the drawn line, the border line, because for every point in that region, the y value is going to be greater than or equal to, if it happens to be actually on the line, 2x minus 4. And we can prove that this is true. We're actually going to pick some points in either region and verify what happens. So just before I do that, the solution, it's really kind of weird to think of it that way, but the solution set to this inequality is represented by the graph I have now drawn. If I'm wondering what points have y greater than or equal to 2x minus 4, well, it's all of the points in the shaded region or on the line. And any points that are not in that region do not satisfy that inequality. So if I pick a random point in the region that I shaded, so where say x equals negative 9 and y equals 7, or no, sorry, y equals 5. And I consider what those points look like inside of this inequality. In other words, is 5 greater than or equal to 2 times negative 9 minus 4? Well, yes, 5 is greater than or equal to negative 22. So that checks out. If I pick another point in there, let's say 0, 0. So x equals 0, y equals 0. Is 0 greater than or equal to 2 times 0 minus 4? Well, yeah, 0 is greater than negative 4. Any point on the line I already know is where 2x minus 4 equals y, so those definitely work. What if I pick a point outside that region? So let's say I have the point 1, negative 9. So x equals 1, y equals negative 9. Is negative 9 greater than or equal to 2 times 1 minus 4? Well, no, negative 9 is not greater than or equal to negative 2, so that one doesn't work. And that would be true of any point that I pick in this region. So essentially what we're doing is we are graphically representing all of the points, and there are infinitely many of them. We're graphically representing all of the points that satisfy the inequality y is greater than or equal to 2x minus 4. The only algebraic way of representing that, incidentally, is with that inequality, is by writing y is greater than or equal to 2x minus 4. Well, what do we do if the line isn't part of the solution? So let's look at an example where that's the case, where I have a linear situation, a linear inequality. X minus 3y is less than 2. Well, I still start by considering where they're equal. So where is x minus 3y equal to 2? And that's going to define a line. Now, to draw that line, I just need 2 points. So I'm going to pick a couple of different values. So let's say y equals 0 is a nice easy one to try out with. So if y equals 0, x equals 2. So the point 2, 0 is on that line. And let's say x is 5. So if x is 5, then y has to be 1. So that point is on this line. And once I've got those 2 points, I can use the slope even once I only had 1 point, but I can just connect those 2 points. And here's what I have. Problem is, those points, the points on that line, are not actually solutions to my inequality. So I don't want them to be represented on this graph in quite that same way. One of the ways that we, on a number line, we can represent that an answer isn't included by using an open circle instead of a closed circle. We used that for points of discontinuity as well on graphs of functions. What we do to show that the line is an important feature of this graph, it's the boundary, but it isn't actually part of the solution, is we make it a dotted line instead of a solid line. So I'm going to use a dashed line instead of a dotted line. So I've got sort of a dashed line like that. That then allows me to draw the boundary while indicating visually that it is not part of the solution to the inequality. Now in this case, I don't have my inequality nicely arranged with a y is greater than or a y is less than. So I can do that. I can rearrange the inequality, or I can just pick points and test them. I really only need to test 1 point. And if it works, that's the region I shade. And if it doesn't work, I shade the other region. But I will test 1 in each region just to be sure. So let's say I test the point x equals 0, y equals 6. So I look at this and I say, okay, well, 0 minus 3 times 6, is that less than 2? Well, yeah, negative 18 is less than 2, so that works. So that tells me right away, this is the region I'm going to shade. But just to be absolutely certain, I'm going to pick a point on the other side of the boundary line. So let's say I have the point 2, negative 2. So x equals 2, y equals negative 2. Now, when you're testing this, especially if you've drawn this line by hand, I pick a point that's not too close to the line, just in case you've drawn your line a little off. You want to make sure that it is very clearly on one side or the other. So then I look at this and I say, is 2 minus 3 times negative 2 less than 2? Well, no, because this is going to be 8, and 8 is not less than 2. So I've correctly shaded the upper region. Now, that's in spite of the fact that this is a less than symbol. And the reason that happens is if I were, so instead of testing points, the other thing I could have done is rearrange this inequality. So I could turn it into negative 3y is less than negative x plus 2. And now when I divide by negative 3, I have to flip the inequality. So that's why that ends up happening. So y is greater than 1/3 x minus 2/3. So that's why I'm shading the upper region, because I'm looking for where are the y values higher than the y values on the line. Two variable inequalities work pretty much the same way whether we're dealing with linear or other inequalities. The only ones you really have to worry about are linear and quadratic, but the same principle applies to any other type of two variable inequality. So you could have something that had a radical or an absolute value or rational expressions. We're just going to limit ourselves to linear and quadratic, but the principles are exactly the same. I consider the line, or not the line, sorry, the associated equation, y equals x squared plus 2x minus 3. This is a parabola. It is factorable, so if I factor it, that helps me see where the x-intercepts are, which can help me draw it. So I have x-intercepts at -3 and at 1. Which means that the vertex has to be halfway between them. So the vertex is at -1. So let's see what we get when we substitute x as -1. Well, we've got 1 minus 2 minus 3, so y would then be -4. So I have a vertex at -1, -4. So now I'm able to draw the parabola, but I'm going to draw it using a dotted or dashed line, because it is not itself included in my inequality. So I just have less than, not less than or equal to. So which region do I shade? Well, I can test points, or in this case, because I do have y isolated, I can say, okay, well, looking at the points I have, the region where the y value is going to be lower than the points I have is the region below that parabola, or another way to think of it here is the region outside of the parabola. So in other words, everything out here. And I could verify that by testing any value in this region or in the other region. I always do like to test at least one point just to make absolutely sure. And so in this case, let's test a really easy one to test would be the origin, 0, 0. What I'm expecting is that that point will not work. So if x equals 0, y equals 0, is 0 less than 0 squared plus 2 times 0 minus 3? Well, no, 0 is not less than -3, so that region doesn't work. So I have shaded the proper region here. So again, the solution to this quadratic inequality in two variables is essentially the region represented by points in that shaded area. Not points on the parabola, although I have to draw the parabola so that you can see where the boundary of that region is. And we'll look at one more quadratic one. This one is given to us in the vertex form, so I can already tell that the vertex is going to be at -3, -1. This one opens downward, so I've got well, I'm going to find the y-intercept too, because then I can get a slightly more accurate sketch. So the y-intercept is where x equals 0, so I've got -1/2 times 3 squared, so times 9, minus 1. So -9/2 minus 1/2, or minus 1, sorry, is -11/2. So we've got an y-intercept right there. And because of symmetry, I'll have that same point over on the other side of the vertex. And this one I'm going to draw using a solid line. So here we go. And because I have less than or equal to, essentially I look at these points and I think, okay, well, where is the y value smaller than the y value on the line? And that will be everything below this parabola, or another way to think of it here is everything inside the parabola. Again, you can do this by testing a point. So I could pick a point, let's say -1, -5. So if x equals -1 and y equals -5, what I'm expecting is that that will work in the inequality. So is -5 less than or equal to -1/2 times -1 plus 3 all squared minus 1. So -1 plus 3 is 2. 2 squared is 4. 4 times -1/2 is -2. Minus 1 gives me -3. And yes, -5 is less than or equal to -3. So I've shaded the right region. If I pick a point outside that region, it will not work. That's the basic idea. The representation of the graphical representation of the solution set basically is all of the points that if I plug in the x and y values to that inequality, it will work. And the graphical way to represent that is using a shaded region on a graph. So we draw the boundary function, whether it's a line or a parabola, or really it could be anything else. And when we draw it, we have to decide if we're using a solid line or a dotted line. And then that will divide the plane into regions. For the functions we're going to look at, it's just going to be 2 regions. And then we choose which of those regions get shaded. So that's the process. To practice it in your textbook, you can look at lessons 9.1 and 9.3.